I'm Mike Wunder, and I'm an animal ecologist who studies bird migration. Mountain plovers, such as those seen in this photo here, have captivated my work life for most of the past 15 years. Migration is a phenomenon that has fascinated people for a very long time. Aristotle believed that during the winter, swallows and kites could be found hibernating in holes in the ground. Swedish Archbishop Olaus Magnus wrote in 1555 that swallows congregate in marshes during fall and then sink down into the water and mud during the winter. Fishermen would sometimes catch them as bycatch in nets, he said. On finding them in these nets, inexperienced fishermen would try to warm them up only to have them die. Experienced fishermen would leave them to return again in the spring. These stories persisted for centuries because it's rare to observe migration in total. However, stable isotope compositions of bird feathers can be used to help understand migratory pathways. The chemistry of dietary items varies in a somewhat predictable way across continental gradients, often because of differences of the isotopes of precipitation. This map, for example, shows the gradients in stable hydrogen isotopes of precipitation across North America. Now, when a bird grows a feather in one location, that feather chemistry reflects the local environmental chemistry where it was developed. Because feathers are metabolically inert, that environmental chemistry is locked into the feather and then transported with the bird as it migrates south for the winter. So the trick then is to use that chemistry to try and figure out how to connect it back to the location where it was developed. And to do that, we need to know the probability of any given location as being the origin, given the feather chemistry and the geographic gradient in the environmental chemistry. Bayes' theorem is used to compute these conditional probabilities. To understand how conditional probabilities work, consider a simple example using dice. If I roll 2 dice, there are 36 possible outcomes. Those 36 outcomes are called the sample space. Suppose I want to find the probability of the sum of the dice equaling 6. Of those 36 possible outcomes, there are 5 ways that the 2 dice will sum to 6. So the probability is 5 out of 36. Likewise, there are 11 ways to get a 2 on at least one of the dice. Then the probability of getting at least one 2 can be considered as 11 over 36. Now, suppose I want to know the probability that I get a 2 on at least one die, given that the sum of the 2 die is 6. In this case, I've reduced the range of possible outcomes from 36 to just those cases where the sum of the 2 die equals 6. And there are only 5 of those outcomes. Of those 5, there are only 2 that feature a 2 on at least one die. So the conditional probability of rolling a 2 on at least one die, given that the sum is 6, is 2 over 5. Now let's consider that problem the other way around. What is the probability that the sum of the 2 dice is 6, given that at least one of the dice is a 2? There are 11 cases, remember, that meet our condition of at least one dice equaling 2. Of those, there are only 2 cases that sum to 6. So here we've reduced our sample space again from the original 36, this time down to 11, and the probability is 2 over 11. Notice that these 2 conditional probabilities are not equal. That is, the probability of B given A is not equal to the probability of A given B. That's because in this example, the conditional sample spaces are not equal. Thomas Bayes wrote a theorem to address this kind of problem. It says that the probability of some event B given A is equal to the probability of A given B so long as B also occurred, and so long as the probability is conditioned on all possible outcomes in A. Using the numbers from our dice example, we can solve for the conditional probability of one set of events, given the inverse conditional probability of those events. So for example, if we plug in the numbers for probability of A, probability of B, and probability of A given B, we find that the probability of B given A can be computed numerically without having to look at the graphics of dice. The application of this principle to our feather assignment problem is just as simple. Although it looks more complicated, the process is identical to what we just did. We want to find the probability of some location J as being the origin of the bird, given the chemistry of the feather and the chemistry of the location. To do this, we need to know the probability of that particular chemistry occurring at that particular location. And that's because not all birds will integrate the environmental chemistry in the same way, here illustrated by the different shades of red for a small population of birds, all foraging and growing feathers in the same location X. Next, we need to know the probability of any location as the origin without using any chemistry. That is, there may be differences in population size, for example, that would normally suggest that a bird was more likely to have derived from a location where more birds were already known to occur. And that's represented with the different shades of blue in this diagram here. Finally, we need the same information for all possible locations of interest in our problem. Putting it all together allows us to provide a range of probabilities to all locations such that we can make informed judgments about the origin of the feather given the feather chemistry and the environmental gradients in the chemistry that were used to develop feathers. It's as though the birds are carrying chemical color markers as they migrate. This video was produced in support of the Spatial short course presented at the University of Utah. For additional information on these methods, please refer to the related videos.